Transformer have become one of the most widely used architecture in both natural language processing and computer vision. Today, in this video, we are going to implement the vision transformer in TensorFlow framework. Hello friends, this is Nikhil Tomar and you are watching Idiot Developer. Make sure to subscribe the channel and hit that bell icon for more such awesome videos. Now let's move on to the presentation. So our first question is, what is vision transformer? Vision transformer, or simply ViT, is a transformer based architecture used in the field of computer vision. It is directly inspired by the use of transformer in natural language processing tasks. So now let us compare the vision transformer with a normal CNN. So in normal CNN, complete image is taken as input, while in the ViT, that is vision transformer, the image is first divided into equal size patches. Here you can see this image has 9 patch, and each of those patch are then passed through some linear layer. The output from the linear layer are called the patch embeddings. Then within those patch embedding we add position embedding. The position embedding we add just to make sure that the model have some positional information about the sequence of those patches, so that model knows that this is first patch, this is second, this is third, like this. So we give a positional encoding to the network. So after we add the positional embedding, we add an extra learnable token. So this extra learnable class embedding we add at the starting of those, the sequence of those embeddings. Okay, so we add this, just add this for the image classification purpose, because let's say at the end of the transformer encoder we get same output. Okay, we get 10 different feature map. Okay, so for classification task we take the output from this first, the class embedding, and we pass this output to this MLP head, and then we do the classification. But let's say we don't add these. Why don't we use output from any of those? Let's say we take the output of this fifth patch from the transformer encoder and use it for the classification. Then we are biased. In this way we are biased toward a specific patch. To make sure we don't do such biasness or unfairness, we add this extra class embedding, and this learns. So over the layers of the transformer encoder, it learns the entire image representation, and that is why we use its output for our MLP head. Now in the transformers, the input image processing is really important. So this is our input image of size 512 by 512. So this is an RGB image, so it has 3 channels. You can see it as grayscale, but we're assuming we would take an RGB image. And then we need to transform it into smaller patches. Let's say the size of patches is 32 by 32. So total number of patches we have is 255.6. So we need this transformation. So now we're going to learn how we're going to transform this, how this processing works, because this is really essential to understand it. Initially even I was a bit confused when I was reading the paper and writing the code. So I've made it easy for you. So here you can see the image processing theory and an example. So we have an input image with a dimension h, w and c. So hw refers to image height and width, and c refers to image channels. And here in the example we have input image of size 512 by 512 by 3. Then we need some patch size. So the height and width of the patch are ph and pw. So let's say we want a patch size of 32 by 32. One more thing here you need to remember is that the patch size should be easily divided by image size. It should be like, just use the rule 2 raised to the power n. That is really efficient. If you work with any image size or any deep learning architecture, just use this. Just remember anything. Remember the formula 2 raised to the power n. Just use that. If you use this, it will be really easy, because if we have a patch size of 32 by 32, this image can be easily divided. Okay. So next we have how many number of patches we would have. So to get this, you're going to take the input image height and width, multiply them, and then divide them with the height and width of the patch. So let's go to our example. Here number of patches n would be equal to 512 into 512 divided by 32 by 32. So this, by solving this equation, we got number of patches as 256. Now last we have the transform input, which we gonna give to the in this our ViT. So that would be n. First we number of patches, then patch height multiply by patch width, then number of channels. So in our example, the transform input would be 256, that is number of patches, then 32, that is patch height, 32 patch width, and 3 number of channel in our input image. And this would become a flattened input of size 256 by 3072. So this is how you transform the image using these simple equations or formulas, and we're going to use them while writing the code for the vision transformer. So just remember, it would make it easy for you to understand. So next we have our transformer encoder, which is one of the basic building block for your transformer. So it first take your patch embedding. So patch embedding is basically your flatten embeddings, and then we add positional information, then we add the extra token. So that information is patch embedded patch. It first passes through the norm. So norm here refers to layer normalization. After that it uses this multi-head attention, which is one of the essential component of the transformer, which makes it really helpful. After that we have a skip connection, or you can say a residual connection. After this we again have our layer normalization, and then we have an MLP, that is multi-layer perceptron. So in MLP we have two linear layer, and in between those two layer we use our GLU activation function, and again we have one skip connection, and this forms the output of your encoder block. So in our transformer we have multiple such encoder blocks. Now we have three different variants of the ViT. First is ViT-Base, ViT-Large, and ViT-Huge, and these changes depend upon the layers, hidden size, MLP size, heads, okay, and according to them we have different number of parameter. So this is all about the theory of the vision transformer. Now let us move on to the coding part. Here we are in our text editor. So first of all, we are going to import all the files or the libraries which we require for our vision transformer. So first of all, we have written the simple line, that is tf cpp min log level. This we have written just to get rid of the TensorFlow messages we would get. After that we have imported the TensorFlow, then we have imported all the layer from TensorFlow. So instead of star you can write specific layer, but here I'm writing star, just I don't have to specifically write each layer, but I'll want you to be sure, just write those specific layer. So in my GitHub code you will get the specific layer names, okay. And after that we have imported this model class, which would help us to build the model, as it takes the input and the output of the model. So now let's start working. So first of all, we're gonna begin with our main function. And here we're gonna write the configuration for our transformer. As you know, there are three different variants of the transformer. So we're gonna have a configuration. So in this video we are going to build the base one, the simpler one. So here you can see all the configuration. So it has number of layer as 12, hidden dimension 768, MLP dimension 3072, number of head 12, and like this. So here we have also specified the patch size and number of channel and also number of patches. So you remember the example, that is what we have taken here, okay. So first of all, let's have our simple ViT class. What the class? The function def. That's right, ViT. Now it's going to take this configuration file, okay. So first of all we need the inputs. So we're going to define an input layer. We're going to give this input layer from the TensorFlow.Keras, and now it would require an input shape. So let us write a variable called input shape. Now we need to define the input shape. So if you remember from the previous video, first of all we need this number of patches. So let's say CF, that is configuration num patches. Okay, after that we need a lot more. First we need patch size or patch height and width. Because both the height and width are equal, so I have set patch size. Okay, so here we're going to say patch size into, let's copy it, patch size, then we have number of channel. So we're going to copy it from here and we're going to say num channels. So this is our input layer. Let's print its shape for now. So when we move forward in the code, we'll try to see the shape of each layer so that we know how the things are transforming. Okay, so let's call our model, call it ViT. Currently does not give you anything back, so it is blank. Let's now run this. Okay, did you mean TF? Okay, my mistake. This should be config, not CF. That's a simple mistake which everybody does. Okay, so this is the input layer shape. So let me just copy it from here and paste it simply like this, so that we get an idea what is the shape of this layer. So next we need the patch embedding. Okay, so I'm going to write patch. We also going to give position embedding. So these are just simple comments just for you, so that you know how we proceed. So for patch embedding, we're going to pass this input to a linear layer, or we can call it a dense layer. So we can call patch embed a dense layer. So for dense is gonna take this 768, that is hidden dimension. Let's call CF hidden dimension. Okay, just that. We are not going to provide any activation function here because we kind of want to get an embedding. Okay, so we don't provide any activation function specifically here. So this forms our patch embedding. Okay, next we need the positions. So in ViT, we don't follow like in NLP we have two dimensional positional embedding. Here we have simple one dimension. We're going to start from 0 and go till the range. Okay, so we're going to say positions tf dot range. So I hope you have used the function range from the simple Python. Here we have tf range, it's basically the same. Okay, just we to specify some value. So start would be 0, limit would be number of patches, that is CF num patches. Okay, and we need delta, that is number of step, that is 1. So now let's print this, and from my assumption it should have values from 0 to 255 because we have 256 patches. So let's print it and see what do we get. Okay, so you can see from 0 till 255. So this is simple position information. This is basically the sequence. Okay, so it has a shape of, you can say, 256. Okay, now position is done. We need position embedding. For that we're gonna use our embedding layer. So input dimension for the embedding layer would be number of patches, and the output would be hidden dimension, output dim, that is output dimension, CF hidden dimension. So remember, this hidden dimension would remain the same. So initially we transform this size into none refers to batch size 256 by hidden dimension, and it would remain same over the entire network. Okay, at the output we would get a shape, patch size by number of patches by hidden dimension. Okay, so it will remain the same. So we have this embedding and we're gonna give it the input, that is position. Okay, so we have this position embedding. Now let's print its shape. I hope this is really easy for you to understand, like how we proceed and what are we doing in each step. That is why I'm printing shape in each step. So you can say this is the shape of your position embedding. So let's put them here. Okay, position embedding is done. Now we're gonna add them. We're gonna say embed equals to patch embedding plus position embedding. Okay, so this is really simple and we are done till here. So now let's print the shape of this embed. Okay, we have some error here. See, patch embed. Oh, if you see this patch embedding, we haven't given any input. So that is a really silly mistake to make. But I hope you will understand that these mistakes are just common when you write code. No one is perfect. So we have got our required shape. So let's note it down. So noting this shape would give us an idea how things transform. Because when you write a network or work on a network, I believe the shape is really important, how the things transform. Because let's say you need some skip connection, you need to concatenate, you need to add. So shapes are important in that condition. Okay, so now we have added the patch embedding plus the positional embeddings. Now we need to add the extra class token. Here we're going to say adding class token, and for this we need a bit of hard work. Okay, so we are going to build a simple class or layer. You can say class, we're going to say token, class token, we can say, not simple to class token. Okay, and this is going to be a layer. Let's define the init initializer. We don't want to give anything, just self is enough, as this is a, I think, the child class and the layer is the parent class. So this, we are done with the initializer. So let's define the simple function which are there in this layer class. So we have the input shape. Okay, then another function call. I'm gonna take the input. Okay, so let's go inside this build. So if you go to the shape, we need just an extra this class token and embedding, you can say, or a tensor, or what you call it, it's same. So it should be of size, batch size by 1 by 768. Okay, that is the exact shape we want. So first of all we need a variable, and to build a variable we need the initializer. So how we going to initialize it? So for now we're going to initialize it randomly. So you can initialize it as 0, 1 or what you want. So I'm just going with simple, the random initializer. So here we're going to say tf.w. You can give it any name, variable. Okay, so we're going to give initial value equal to w init. Then we need to give shape here, that would be 1 1 and the input shape. Okay, so if we see this shape, we're going to give this shape as the input. So this would be input shape -1. See, we give 1 here because we're going to change it to batch size. Okay, this one, just that extra embedding, and that extra embedding would be of this much size. Okay, let's give the data type here, that is also important, that is tf.float32. Okay, now because we want it trainable, so we're going to have another variable here, trainable, and we're going to set it to true because we want it to train, because we're going to use it at the end for our classification. So our build function is complete. Now we're going to move on to the class Okay, so from this input we're gonna first extract the batch size. So just remember one thing, be just try to use this, do not use like input dot shape dot zero, because that don't work. I've also used it, so just don't take it lightly. Things are a bit complicated when you work with TensorFlow in comparison with PyTorch, because I'm also using PyTorch recently for some of my research paper. I feel PyTorch is much easy to handle in comparison with TensorFlow. But TensorFlow is great because of its production capabilities, because you can use it in Android and a lot of other things. That is what I believe. If you are in a research and want to build something just for research, then PyTorch is okay. Even TensorFlow is okay, but I prefer PyTorch. But when it comes to production, I go with TensorFlow then. Let's say you want to implement something, then I believe TensorFlow is really good. Okay, so here we're going to extract this hidden dimension from this input. So we're going to say hidden dimension. See, there are two ways. Either you can say inputs -1, or you can extract it from this. So I'm going to extract it from the variable only, just to be sure I have the same thing, -1. Okay, now for once let's call this class. Maybe we're gonna have some error here. Let's see what do we have. So we're gonna call it token. Okay, that is the class name, and input would be embed. That is this. We're gonna give this input because we require the shape. Okay, that is why we even this layer does not require any specific input. Okay, just because we want that shape, that is why we giving it that input. Okay, so now let's do one thing. First of all, let's print these two things, that is batch size and hidden dimension. Let's see what do we get. Maybe we get an error or anything, but let's see. Okay, we have something, some tensor here, some tensor value, and it's specified 768. Okay, so now let's now we're gonna use some function from the TensorFlow, that is tf.broadcast. So we're gonna say class tf.broadcast self.w. Then first we use the batch size. This is where we specify that specific size which you want to give for our class token. Then 1, then hidden dimension. Okay, and after that we're gonna cast it. Same as the inputs. And we're gonna give it back. So this is our token. And we have set trainable to true, so this is gonna learn over time. So we have got our token. Now we're gonna append it to the, not append is basically at the end, so we're gonna add it to the starting. So this is going to be the first thing in the sequence of all the patches. So we're gonna say x, then concatenate, and the token would be the beginning. Then we have the embed, and on the first axis, okay, should be like this. Okay, so now we have our input for the tensor, for the transformer encoder. Now let's print the shape. I hope there would be no error while adding these, like concatenating these, not adding. Okay, so you can see from 256 we move to 257, so to 257. So at the 0th position, just remember at the 0th position we have our class token. Okay, and the class token is used for image classification, just that simple. Okay, so now we're going to move on to the transformer encoder. Let's write it. So in for transformer encoder, it's going to be repeated this much time. Okay, so before moving on to that, let's build a specific function, okay, for transformer encoder, because we don't want to repeat same lines again and again. Let's build a function that would be easy. So it's gonna take the input and this configuration. See, this configuration makes it really easy. Now we just need to give this and we have all the information inside it. We can get them whenever we want. But if we give 10 now 10 variable, then it's gonna make it difficult to handle. So this is, I feel, really easy way. So first we have this skip one. Okay, so let's let me just show you the diagram. Okay, just please be with me. This, okay, so this is the original paper and this paper is accepted in ICLR 21, and ICLR is really good conference. Okay, and one of my recent paper is get accepted in MICI 22. I've attended that conference. That's really nice. It's my first conference and I'm really happy. Was really happy. Okay, now let's okay, so what do, okay, we need the transformer encoder. Okay, this we need this diagram. So first we have this normalization and multi-head attention, and this input would be added to this. So this is our first skip connection. So we're gonna have skip 1 equals to x. So we save it initially, then x layer normalization. By the way, I've also written a blog post or a simple summary of the architecture of vision transformer on my blog idiotdeveloper.com. Just do check that out also. So this is our layer normalization. Then we need multi-head attention. So in TensorFlow, we already got the implemented version of multi-head attention. So we're going to use that. So first of all, it requires num heads, spelling mistake, configuration, num heads. Okay, then key dimension, that would be hidden dimension, that is going to remain the same. Okay, and its input would be x and x 2 times. After that we're going to add x with a skip 1. Okay, so this is done. Now let's move back to our diagram. Where is that? This. So we are done with this. Next we have normalization and MLP, and this addition would be skip 2. Okay, so let's call it skip 2 x. Then we need layer normalization again. Now we have MLP here. See, MLP, that is multi-layer perceptron. So we haven't built a function, so we're going to build it. So let's define it right here. X would be input, then configuration. Okay, let's assume this is this work is done, MLP is done. So now let's assume I'm going to build it later. So after that, let's again see, after MLP we're going to add them and we're going to get our output. Okay, so after MLP we're going to say add x, then skip 2, and we're going to give this x back. Okay, so now we need to build the MLP. So let's build it at the top, the transformer encoder, MLP. This is really simple. So we need a dense layer. The number of input units would be MLP data dimension, number of unit. So in TensorFlow, when you give this MLP dimension, this means the number of output features, and here activation would be GILU, input x. Then here we have a dropout, input x, and we have a dropout rate. Again we have a dense layer, or you can call it a fully connected. Now the output number of feature would be hidden dimension. As you remember, hidden dimension would remain the same all over the network. Input x, and again we have a dropout, and we give it back. So this is our simple MLP. So we have implemented both the MLP and the transformer encoder. Now let's move on to the ViT. So here we're going to have a loop because we need to repeat the transformer encoder 12 times. So we're going to say for underscore in range, and that would be CF num layers. Okay, now here we're going to use the transformer encoder, initial input X, then CF the configuration, and we are done here. So now let's print the shape of this X. So just remember the initial shape, okay, of the input. Okay, we don't have this shape. I remember. Just remember this shape, that is 257. Now remember this shape and check this shape. They both would be same. See, exact same, because this number of patches would remain the same and this hidden dimension is already the same for the entire network. So after this, we got the output from the transformer encoder. Now we need to use it for the classification. So we're gonna have a classification head here. So first the output would be followed by layer normalization. Again, X. The shape is going to be same. Let's print it here. Now, if you remember, we have 257 shape and we have added this token. Okay. So what do we want? We want the first token, the class token from this 257. So how are we going to extract it? We're going to say X. So we're going to simply splice it. So we have three things here. First, batch size, then this the number of patches or the sequence, and number of feature or the dimension. So first, batch size we don't want to touch, so it's going to remain same. But from this 257, we want the first one. Then third dimension we don't want to touch. So this way we have extracted the one we required. Okay, I'm a bit confused whether this would be 0 or 1. So let's, because I generally forget that things begin with 0 in this. Okay, let's see. If we get an error, this means should begin with 1. I am a bit confused here. Let's just run the program and see. I think 0 should be an error. Okay, so in splicing we began with 0. Yeah, we began with 0. Okay, so we are right. So we extract that token, that learnable token at the end, and then we remain with 256. If we remove this, then we left with 256 patches. So we don't want to use the output from patches, otherwise we would be biased toward a specific patch. That is why we have added this class token. Now we have this. Now what we're gonna do, we're gonna add a dropout. So let's print the shape before. Okay, we have printed this, we just haven't copied it. Let's paste it here. Okay, now we're gonna add a dropout here. 0.1 X would be input. Then we're gonna have a dense layer. Let's say we are working on some classification data set like CIFAR100, for example. This video just for implementation. In next video, maybe I'm gonna do image classification with this ViT. For the dense activation would be softmax, because we are working with multi-class classification. Okay, so now if you see, we have this input and we have this X as the output. Now we're gonna build the model. We're gonna give it back. So this is our entire ViT, that is vision transformer. So let's print its summary. Okay, please. Let's run it, and finally hoping it would run. Okay, so at the end you can see a dense layer with 10 as the number of feature representing number of classes for our classification purpose. And if you see, this would remain the same, just inside this the MLP it would change, otherwise it would remain the same. Okay, so this is our initial input, and now I think you would understand why we have this 256 by 3072. The initial image size is 512 by 512 by 3. 256 refers to the number of patches and 3072 refers to patch height multiply patch width and number of channel. Okay, and this is the entire set of layers we have. Okay, so this is all about the vision transformer. I hope you found this implementation helpful, and I'm not saying this is absolutely the correct and the same implementation that is proposed in the paper. Maybe I've made some modification by mistake, or I've left something out. So if you feel something is left, just please comment it down, or if you have any error, any query, any question, anything you want to ask, just write it down. And the link for this code would also be in description. Just check the description, a lot of link would be there. And if you have reached until this part of the video, then I believe you have found this useful. So make sure to subscribe the channel, hit that bell icon, and do share the video, subscribe the channel, and do a whole lot of stuff that all other YouTubers say. So thank you, have a nice day.